Hello everyone, myself Dr.N.Marimuthu, Associate Professor, Department of Physics, Bharat Institute of Higher Education and Research. So in this lecture, we are going to see mechanical properties of solids. So every engineering student should have a knowledge about the properties of material. Why? Because if you are going to choose any material for any applications, if you don't have a proper knowledge about properties of material, you can't select the suitable material for particular applications. So every engineering student should have the knowledge about the material. So in this video, we are discussing about only mechanical properties of solids. Then what is matter? Any substance that has mass and takes up space by having volume, we can say it's a matter. So we know already very well three types of matter: solid, liquid and gas. So other than these three, other matter is also possible. One is plasma, then another one is Bose-Einstein condensate and fermionic condensate and quark-gluon plasma. So these are all the another states of matter. You just know about remaining things of matter. Okay, but here we are going to discuss about only solid. You know very well what is solid. We just move rigid body. What is, when we consider solid, the important thing is rigid body. So what is rigid body? When a force is applied on a body, there will be no change in the shape or size. That is called rigid body. If suppose we are going to apply any force on a material, the dimension of the body is not going to change, then we can say that body is a completely rigid body. But there is no perfectly rigid body in the universe. Does not exist in the universe. Okay, some microscopic level, the dimension going to change when we apply any force on that material. Okay, so we just macroscopical level we consider some bodies are rigid body, but in real there is no rigid body in the universe. Okay, then elasticity, the important properties of solids. Okay, one of the very important properties of the materials, elasticity. So before these things, I am going to ask one question. So here I am showing rubber and steel. Do you know which one has high elasticity, rubber or steel? Guys, in our day-to-day life, we misconcepts rubber has high elasticity. Suddenly it comes in our mind, correct? But based on science, the steel has high elasticity compared with rubber. Then what is the elasticity? You just know about the definition of elasticity based on the science, then you can easily understand what is the elasticity and how the steel has high elasticity. We can easily understand. You just think about this, how the steel has high elasticity. In our daily life, we think rubber has high elasticity, but here he says steel has high elasticity. Okay. After this session, you can analyze how the steel has high elasticity based on the science, not our day-to-day life. Okay. Here, what is elasticity? What is elasticity? Elastic materials or elasticity, it is nothing but the ability of an object or a material to resume its normal shape after being stretched or compressed. Now, if you are going to apply a force on any material, if you are going to elongate on any material, it will be going to elongate. Then when we remove our applied force, the material regains its original shape. The material which are having such a kind of property, then we can say that material is elastic material. Yes, after removal of applied force, the material should regain its original shape. The proper definition of elastic material: it is a tendency of a material to regain its original shape after removal of applied force. Then we can say that is a definition of elastic material. Okay. If any material is not regains its original shape after removal of applied force, then we can say it's a plastic material. So here the rubber, the steel rods are the examples of elastic material, and the clay and mud are the examples of plastic material. So when we applied a force on this clay materials, okay, it's after removal of our applied force, the material is not comes to its original shape, right? So it is the examples of plastic material. The another definitions also there for elastic material. Okay, that means the tendency of an object to oppose any change in its shape or size or their dimension, that is called elasticity. Okay, the tendency of an object to oppose any change in its dimension. So based on this dimension, you can conclude steel has a high elasticity, correct? Steel has high elasticity because it more opposition than rubber, correct? When we applied a force on that material. Okay, just thinking about which one has a high elasticity, rubber or steel. Okay. Then how the elastic property which is present inside the material, why the material regains its original shape after removal of our applied force? We know very well all the materials made by atoms. Okay, so all the atoms are arranged. You just take this picture. Okay, so the black dot, it is nothing but just considered an atom. Okay, so between the atoms, we know that all the atoms are connected by the chemical bonds. Okay, the bonds act like a spring. So we know very well the properties of spring. When you compress the spring, it will be going to compress. Then after removal of our applied force, the spring regains its original shape, correct? Then when we are going to elongate the spring easily elongates. Then when we removal of our applied force, the spring also regains its original shape, correct? So the chemical bond acts as a spring between the molecules or the atoms, correct? So when we apply a force on the material, okay, here all the atoms are connected by the springs. Okay, so all the springs going to compress. Then when we removal of our applied force, okay, the material regains its original shape due to the spring action, correct? So that's why some material having elastic properties, correct? Then here, which one has high elasticity, rubber or steel? So if you want to know this solution, which one has high elasticity, you just understand some fundamental concepts. Okay, so after understanding that fundamental concept, you have to find the answer. That is nothing but stress and strain. So the stress and strain completely related to the elastic properties. Okay. Then what is stress? Stress refers to the cause of deformation. Cause of deformation. When we applied a force on a material, the dimension of the material going to change. Correct? So the force, the applied force, change something on the material, that it creates some cause on that material. The mathematical expression for the stress is force by area. Stress is equal to force by area. You can think, yeah, pressure also force by area. Then what is the difference between stress and pressure? Because both are having same formula, you know. This force here, this force, it is a restoring force, not applied force. When we applied a force on a material, okay, our applied force stored as a restoring force. See, if I am going to elongate the material, okay, like this, okay, if I am going to elongate the material, okay, it will be going to elongate. Then after removal of my applied force, then who bring the material to back? Okay, so whenever the material regains its original shape, it needs force. Otherwise, the material is not regains its original shape. Correct? Okay. So here the material going to elongate because due to my applied force. Then after removal of my applied force, then which force bring the material back? That is restoring force. So when we applied a force on a material, our applied force stored inside the material as restoring force. Okay, this force developed inside material, not applied force. Clear? So stress is equal to restoring force by area, not applied force by area. If you consider applied force by area, that is equal to pressure. Clear? Here we consider the restoring force, not applied force. But generally the restoring force 99% equal to applied force. Clear? Because we just going to calculate, we already know what is stress. See, our day-to-day life, what is the meaning of stress? Okay, the stress created inside our body, not outside. Correct? See, I feel some stress in my body or in my brain or in my head. Okay, so the stress, okay, indicates something will arise inside the body. Correct? Likewise, here stress is equal to not applied force, restoring force by area. Restoring force by area. So clear about this one, because don't confuse with pressure and stress. Okay, so stress, force by area. Then what is the unit of stress? Newton per meter square. Newton per meter square. Then so stress is the cause of the deformation. Then another important term is strain. And what is strain? Strain refers to the effect of the deformation. Then what is the effect? Then what is the effect? The change in length. That is the effect by the due to that stress. Correct? So the mathematical expression of strain is equal to change in length divided by original length. the ratio of the change in length to the original length, that is equal to strain. So mathematically the epsilon is equal to change in length is equal to del L, then original length is equal to capital L. Okay, so here you just consider this diagram. If I am going to apply a force F, applied force, the change in length is equal to small x. Then what is stress? Stress is equal to restoring force by area. Then what is the area of cross section of this material? Okay, if you are going to take a cylindrical rod, okay, area of cross section of the rod is equal to here, this area. Okay, so restoring force by area, you don't think this is not applied force, we consider only restoring force. Okay, you just clear about this. Then strain, change in length divided by original length. Okay. Then types of stress. There are three types of stress. Then one is longitudinal stress, then shearing stress, then volume stress. Then what is the longitudinal stress? In longitudinal stress, it is a restoring force by area of cross section, that is common for all the three types. Here the change, the stress going to applied in a linear, okay, that is equal to longitudinal stress. There are two types of longitudinal stress. One is compressive stress, then another one is tensile stress. Okay, if you are going to apply a force on a material, that force compress the material, that is compressive stress. When you are going to elongate, that stress is called tensile stress. Okay, then shearing stress. And what is shearing stress? The stress going to bend the material. The stress is not change the shape of the material in single direction, linearly. It's not going to change linearly. So instead of linearly, this stress going to be bend the material. That stress is called shearing stress. Okay, so here shearing stress mathematically expressed force by area. Here the angle. Here some angle going to bend, okay, that angle, the tan theta is equal to shearing stress. Here, tan theta is equal to shearing stress, because the ratio between this del x and the original length is equal to shearing stress. Okay. Then what about volume stress? The stress going to be change the total volume of the body. Then we can say this is volume stress. So initial volume of the body is equal to V, then after some applied force the volume going to be changed, that is del V. Okay, so volume stress it is nothing but again the same formula, force by area of cross section. That is that area of cross section. Here we consider circumference of the circle. Correct. So the area of cross section, it is depends on the materials. Okay, it's not constant one. Okay, so there are three types of stress. One is longitudinal stress, another one is shearing stress, and then another one is volume stress. The stress which is applied linearly, that is longitudinal stress. There are two types. One is compressive stress, another one is tensile stress. Then when the stress going to create the bending effect on the body, then we can say it's a shearing stress. Then when the stress affect total volume of the body, we can say that is volume stress. Then there are three types of strain. One is longitudinal strain, another one is shearing strain, then volume strain. Then what is a longitudinal strain? It's like three types of stress. So longitudinal strain, it is nothing but the change in dimension only affect the length then we can say it's a longitudinal strain. Then change in length divided by original length. Then shearing strain. So shearing strain, the strain going to affect the total, not only the length, correct, it is also going to affect some breadth also, that is it going to create some bending. Okay, so here the change in length, here the x. Okay, so what is the original length and then what is the change in length? So change in length divided by original length, again it is also having same formula, shearing strain. Then what is volume strain? The change in volume divided by original volume. Change in volume divided by original volume, that is volume strain. So here change in volume, that is del V, then sorry, V minus del V, then original volume V. So V minus del V divided by V, that should be equal to volume strain. So there are three types of strain, then three types of stress. Here, if I am going to take same material, okay, you just consider steel, okay, or any material, you think any material, okay, same length, same area of cross section, okay. If I am going to apply different force on that material, the first material I am applied very small force, you just assume 10 Newton force. Then second material I am going to apply a greater force, that is 20 Newton or 50 Newton force. Then which one elongate more? Same material, same area of cross section, same length, but applied force is different. And which one elongate more? Here the change in length, elongation, the change in length directly proportional to applied force, correct? Applied force. So when we applied more force on a material, the material obviously elongate more. If you apply less force, the material elongate is very less, correct? So the change in length directly proportional to force. Then comes to next. See, initially I am going to take that same material, same area of cross section, but difference in length. The first material is very smaller length compared with the second one. Just assume this is 1 meter, this is 2 meter. If I am going to apply same force on the material, same force, the force is same, not different. Okay, the length only changes, same area of cross section, same applied force. Then what is the change in length? What is the dl? So the dl directly proportional to L. Directly proportional to L. Yes, obviously. Initial length of the material is very large. When we applied a same force on these two different material, the material which one has a high length will elongate more, because change in length directly proportional to L. You can check practically. Okay, you check practically. We know very well in our school days we have a eraser, correct? If you have a large size eraser, we can if you pull the eraser, it will elongate more. If you are having very small size eraser, if you are going to pull it, it's not going to easily elongate, correct? So the change in length depends on the initial length, correct? So more is the length, more is the elongation. So dl directly proportional to L. Then here. So the length is same material, same length, but here I am going to change the area of cross section. Different, area of cross section. If I am going to apply a same force on this material, same force, 10 Newton assume, then what is the change in length? Which one elongate more? This one or this one? Here, the change in length inversely proportional to area of cross section. Correct. Which one has less diameter and less area of cross section? Going to be elongate more compared with large size. We already know that. Okay, practically we think. Okay, when the bar is very, if I am going to take a steel bar, okay, this size and a very large one, and we easily elongate this smaller diameter, okay. So the area of cross section is very less, the elongation going to be large. So DL inversely proportional to area of cross section. Clear? So from the three examples, the DL directly proportional to F, and DL directly proportional to L, and DL inversely proportional to area of cross section. Then a small rearrangement here, DL directly proportional to F, L and A. F here, restoring force, not applied force. Clear? Because 99% the applied force equal to restoring force. Clear? So after small arrangements, okay, I get F by A divided by DL by L. We know. So this F by A then DL by L is equal to constant. For a material, the ratio of this F by A to this DL by L is always constant. We know very well the F by A, it is nothing but stress, and change in length divided by original length, it is nothing but a strain. So for a material, stress by strain is always constant. That means stress directly proportional to strain. That is Hooke's law. This C, it is nothing but modulus of elasticity. So this modulus of elasticity is constant for a material. This modulus of elasticity going to be changed with respect to material. Clear? So here stress is directly proportional to strain. So that is Hooke's law. Can we write strain directly proportional to stress? We can't. Always stress directly proportional to strain, not strain directly proportional to stress. The modulus of elasticity, stress divided by strain, not strain divided by stress. Why stress directly proportional to strain, not strain directly proportional to stress? Because for stress we consider only restoring force, not applied force. Okay, so when the restoring force is developed inside the material, when there is any change in the dimension of the material, then only the restoring force developed inside the material. Okay, there is no change in the shape or size or the dimension of the material, there is no restoring force which is created inside the material. So which one is first? Strain, then only stress. That's why stress directly proportional to strain. Okay, so suppose if you are going to consider applied force, then the formula should write like this: strain directly proportional to stress. Because when there is applied force, then only the body dimension going to change. Otherwise the dimension of the body is not going to change when we consider only applied force. But here we are not consider applied force, stress. I already said it is nothing but restoring force by area. When there is change in dimension, then only the restoring force developed in the material, otherwise it is not. That's why here the stress directly proportional to strain, not strain directly proportional to stress. Keep in your mind, don't change this Hooke's law. Okay, always stress directly proportional to strain. Clear? Okay, thank you.